groups that were not necessarily helpful for his life. And he came here and played football instead. And so, already a hero, right? Just facing that struggle, staying out of things that might harm or shorten your life, right?
Yeah.
That's a big struggle. It's a big choice every day. It's a new pathway. He's going where people didn't go. That's what a lot of us are doing. We're going where people before us didn't go. We're the new explorers. You're leaving the comforts of your imposed society to move forward. It's very tempting to give up, but it's very rewarding not to. Okay, so this class, I know you guys are moving on. It's not first semester, not first class. Stress, fear, mind killers. Where's that from? Anyone? Frank Herbert in Dune. Right? Fear is a mind killer. And it really is. Stress is a mind killer. Right? So if you, instead of relaxing into this great experience of learning chemistry and finding out as much as you can, and just going, wow, look how much I got. I'm going to give you 1,000,000 times more information than you need to pass this class. You're not going to get all of it. You're not supposed to. Some may get all of it, but I mean, that's not how you get through. But it creates a recurring pathway. So if you're constantly going, oh my God, I can't do all this, that's true, right? You're creating that pathway, and it gets more and more leverage as the semester goes on. And it's harder to write that shit. And that's a chemical process. We're not going to talk about that chemical process, unfortunately. But if you're calm, well, my calm and your calm might be different. You're in a learning mode pathway, right? And you're going to establish that pathway. If you keep going, wow, I don't have to be here, but I am, and I'm going to get as much out of this as I can. That's a pathway too, right? And if you relax into it, there's science behind it. I don't know what it is, so I'm going to call it woo-hoo. Right, this is my woo-hoo. I haven't brought it into science. I'm not backing it up with any facts. I'm just saying my experience tells me there's a guy, does a podcast from Stanford. He's Huberman. He has all this stuff. So if you want to listen to him, pick up more of this epinephrine pathway and serotonin pathways and why it's important to stay calm, you can do that. Arthur Huberman, Huberman. He's got a great podcast. He gets a little bit, well, never mind. You can figure out for yourself. He's putting out free information that you would get at Stanford by paying thousands and thousands of dollars to be in this class or the lab. All right. So your outcome will be based on a lack of stress. Right? So when we come in here, you start thinking, doesn't matter, I'm just going to do the best I can, and I'm going to show up. And if I do those things, I'm going to learn something, whether I pass or fail. And pass or fail doesn't become important. What becomes important is showing up and relaxing into the information. Okay, so do you doubt my knowledge of the subject? Yes or no? Do you think I want you to succeed? Yes or no? So the solution is, believe you can, no time to doubt yourself. I don't have time to doubt you. And your time is more valuable than mine, therefore believe. And minimize the doubt that you're going to succeed. Right? If you start thinking about whether you're going to succeed, that's taking time away from doing the things that you have to do to succeed. Right? And that's a pathway. And those chemicals that we start doing and using for energy to do what we have to do, like we're not going to do it 100% anytime. But we're going to do it more effectively if we, instead of, don't say, oh, I don't need to doubt, just put that energy towards, I'm going to focus on this problem right now. And yeah, when you find yourself, you just check it. You go, oh yeah, I can do this. And then go back to doing the problem. Easier said than done, especially if you develop that pathway over 18 years or 20 years or more. So use effectively, use your time outside of class. Little problem on the recommended textbook whether it's recommended or required, right? Two different words. I'm not going to tell you it's required. It's not required. The textbook is not required. It's recommended. I provide all the questions that you need to do this class effectively using the recommended textbook. All right, that's as far as I can go on that. Link to good OER is on the front page now, and that is 2E Adams, great chemistry book. And then if you still are interested in the textbook, then you want to try Books for Bulldogs. Is another place to get it. Another place you can get textbooks often is Mesa and STEM, but that's on the San Diego campus. Okay. So that's enough of that stuff. Any questions so far about anything besides where we find information for the lab aid? Now, this is going to be your thing.
Yeah.
Think of something chemical.
Me?
Yeah?
Something chemical.
Yeah.
Ammonia?
All right, that is a chemical. Great.
Okay.
Bleach?
Okay. We used that in organic yesterday. So bleach, yeah. And it's sodium hypochlorite.
Hydrogen peroxide.
Hydrogen peroxide. So we're coming up with chemicals.
Cleaners.
Cleaners.
Sure.
Hydrochloric acid.
Okay, so now it's a pattern, right? I said name something chemical. We're naming chemicals. Burning. Yeah, oxidation, right? The process of burning, oxidation.
Stress.
Yeah. Whew. Right, good one. Right, we just talked about that. Jack.
Change in color.
Right, color change indicates a chemical reaction. Sometimes it's provided just by the energy of the light. Kaylee? I'm sorry, I got two bad ears. Oh, phase change. Anyone? Could that be a chemical or a physical property?
Physical.
Physical property. Now, the difference between a chemical property and a physical property is one is a change of state, solid or liquid. It's a chemical process, though. We still loop it in there, so it's valid. I'm not saying it's not valid. I'm just saying it's a physical property that we're talking about. Change of state. Okay? Ooh. Well, there's a change of state taking place, right? And there's a process, a physical process. And we're dissolving, right, something to make it move. So, yeah.
An isotope? An isotope?
An isotope?
Yeah.
Yeah.
With different neutrons?
Sure, right? We have a different chemical, a different element with a different number of protons than the other element. No, all elements have a different number of protons. Let's get this right. All elements have a different number of protons. An isotope has a different number of neutrons. Okay. Nate?
Fireworks?
Yeah, one of my favorites. Things go boom, right? You're using all kinds of processes. You're using directed energy when you light it. And you have a bunch of metals inside that when they burn, they release a certain color. And I think we get to do that in lab. I think we get to do a metals lab where we get to see different flame colors. Great one. Adrian?
Fermentation.
Ooh, yeah, another good one. Fermentation.
That's my
Right?
favorite.
Yeah.
We all like that one.
Yeah, in the second semester organic lab, they do a fermentation, they make ethanol, right? And they put it in a hood for a week, grow some yeast. Anyway, so awesome, good one.
Mine is like,
And it's Kaylee? Kylie, sorry, Kylie. Rust, yeah, more oxidation, right? Changing on the surface of a metal because of its exposure to oxygen. Baking soda and? Ooh, yeah, right? A neutralization reaction, acid base. Very good. And your name again? Brenda, thank you. Shannon?
Sydney.
Sydney?
Yeah.
Okay, I'll go with that.
Covalent bonds.
So covalent bonds. Yeah, right? That's how we describe the interaction between elements, either covalently or ionically. And that's the only two choices, right? Either they're going to share electrons or they're going to, take them, right? Or give them. I mean, how can you tell, right?
Oh, gasoline.
Gasoline. Yeah, however you want to use it, right? Used to be guys will wash their hands with gasoline. We don't really do that anymore because those guys died. And man, not so good. And your name was Amy. Sorry. Yeah, anything to do with temperature, right? We use temperature to figure out whether gases are going to separate faster, whether we're going to heat a reaction. So anything to do with temperature. Get hot in here now, all right? And you are Jennifer. Emmanuel. Yeah, right. We can use our olfactory senses to determine whether something's progressing in a reaction or whether, you're melting plastic. That's why we use hoods a lot in chemistry, right?
Natural light.
Ooh. Right. The combination of all the colors? Sure. Right? There's chemistry involved in that. I just hope somebody comes up with one that isn't, but it's not going to happen, right? Because it's essential science. Go ahead.
Two people falling in love.
Oh.
Ooh, there's a good one, right?
Whoa, that was deep.
Whoa. Yeah, right? The chemical process and the release of endorphins and all kinds of pheromones, and it's nice. And then you realize who they are. And you're like, oh. Oh, wait, no, that doesn't happen to you guys. That only happens. Make-believe romance. All right, so, good one.
Okay, like solubility.
Yep. Right? Can you dissolve something in something else? Right? Yeah. So we start thinking about all these processes, and all these things do the same thing. They describe the world around us and what is happening. Ben. Sure. Perfect. Right? How many of these go with how many of those? Does it take 7 guys to play football? Does it take 11? Does it take 5 women to play women's basketball, or does it take 10? I don't know. So.
What if you like going to rehearsal and getting your hair done? Is that fun?
Sure. Especially if you have any process applied to it, like straightening or coloring or cutting. How could cutting be a chemical process? What happens?
Breaking bonds.
Yeah, exactly. You break the bonds that hold your hair together. You don't think of it that way, but that's what it is, right? You're using energy to change the relationship of a strand of hair. Okay, so that's good. So that's what I was trying to show, is that no matter what we talk about, you can break it down and bring it back home to chemistry, and that's why I love it. So normally, I post the lecture slides before the lecture, but not today. They're up there, but it was just right before the lecture. So, and then that way you can, familiar. Here's the thing. The more you do before you get here about what we're going to do, the easier this class is. The less stress you cause yourself, the less seat of the pants stuff you do, and the more you can get into it, or the more make it easier on yourself. And for mostly, all we're going to do here is, if you had my 120 class, is we're going to change the level of problem. We're still going to cover the same material. We're going to go into maybe a little bit more depth, maybe not. We're definitely going to do better experiments. Wow, is that?
You just gave me one.
Yeah, I can see that. So there was this guy named Larson back in the day, and the DDDs and the da-da-das and the... Anyway, periodic table, that's how we measure what things are made of, right? That's the whole purpose of the table, is to say, okay, what are our building blocks? Like if we just took all things and said, how many electrons does it have? Well, we wouldn't be able to, we'd run into problems because some elements have more, let's say it the other way. Some elements have the same number of electrons. Some elements have the same number of neutrons. But the one thing they don't have the same number is protons. And so that's what we organize the periodic table with. How many protons do you have? So chemistry is the study of the properties and behavior of matter. And what is matter? We know that as anything that has mass and occupies space. And everybody matters. We know that. It's the beauty of the English language. The words can mean anything. Why do we study it? Why is it required for so many majors? Why do we do that? Oh, it's to weed people out, really. Because in the old days, chemists were these nasty men who were treated horribly by society, and they took it out on the people that came through their class. I vowed to change that, but it turns out I'm just like them. Everything in the world is chemical. That's why. Everything. One of the reasons you want to study it is because you want to know what is toxic. Yeah. Should I eat that berry? Should I eat that mushroom? Should I walk away from my drink in a bar? Oh wait, no, don't do that. Harmless. Oh, it's harmless. I can eat as much of that as I want. It's like candy or something, but candy's not harmless, it turns out. Is it reactive? If I put two things together, do they mesh? Is it okay for them to sit next to each other, or are they going to be attractive and create a distraction? What's going on, right? Oh, it doesn't react. Inert, that's what that means. Doesn't react. So, I can put this thing anywhere and it'll stay exactly the way it is right now. It's inert. Right? Is it useful? What can I do with this? Is it useless? Like toxic waste. I really can't do anything with it, I better bury it. So that's what we do. And then somebody finds it and goes, oh my God, this is toxic, we need to clean that up. And then you go, well, how are you going to do that? It's toxic. So that's a whole field right there that you can go into that's underexplored. And the reason why? It's toxic. It'll kill you. So one of the things that we have right now as a debate in society is what kind of energy should we use? The problem is lithium, in order to get lithium, you have to destroy the earth and dig it up, and you have to use child labor, allegedly. Nuclear plants are awesome. They're the perfect example. But the problem is there's radioactivity, and mankind is not impervious to radioactivity. And so you pay a guy a lot of money to go to a plant and scrub down the reactor walls. But he can only do it for like 2 or 3 years, and then he has a lifetime dose. But over that course of that time, he made enough money to have a good 10 years, right? So there's a trade-off, and that's one of those things that we keep trying to push down that's real. Life is dangerous. People, human beings, do dangerous things and risk their lives so that a lot of people have a good life. So there's sacrifice going on, right? And we tend to forget about the guys the people because it's all people, human beings, sacrifice for others. And okay, that's it. Oh yeah, to reduce ignorance and fear, right? That's why. That's the real reason. That's the best reason there is. If I share with you what's not toxic, what is toxic, what we can expect to do, what's the lifetime expectancy of the job you're performing, what chemicals need to be isolated, which chemicals can be together, now all of a sudden our society is more harmonious. And this, these slides are old, right? These are pre-COVID slides. And look what's happened with the hype, right? People are scared. Why? Because they don't really understand. They haven't had to sit through and filter out with their minds what's going on. And so there's a mass media hype, and then that frightens people, and that creates fear, and, well, of course it does, and ignorance, because they're not being able to explore all the options, and then there's peer pressure. Okay. So that's a good reason to be here right now. What's the other reason? Chemistry is like a central science. You say that, but everything breaks off of it, right? If you look at biology, biology is just chemistry of life, right? And as biology grows and grows and grows, they keep creeping back to chemistry. Right now, this virus thing, right, is a bunch of proteins reacting with each other, and the order of those proteins. Well, that's all chemistry, right? What happens, what would chemists study? Chemists would study what happens, what's causing the reaction between these protons to be different. Why is the shape changing? What are the characteristics? How much does it weigh? Can we reproduce it over and over and over again? But that's become a biological field. But it's still chemistry, and environmental science, and geochemistry, and nuclear chemistry, and nanoscience, and material science. So there's a huge field out there, and don't just dismiss like what we're learning here and saying that's all of chemistry. That's why chemistry is the starting point, is because all these things grew out of chemistry. It used to be there was just chemistry and physics. And then this thing called biology, which wasn't really a science then, it's like woo-woo stuff now, right? Right now, energy work is all the woo-woo, but it's being drawn in because there's so many people studying it, and now you have thousands of people reporting data, and now it becomes real, right? And that's all this is. All science is explaining what we understand, not what we don't. And as we understand more, we get a more cohesive view of the universe. All right. Central chemistry theme. We have macroscopic properties, what you see, what you measure. Our substances are dependent upon microscopic properties, which you don't see. And that makes sense, right? What we see is this giant fan here circulating air, and right, ignorance and fear. This is a 1 micron filter. The particles we're trying to protect ourselves from are submicron or nano-sized particles. Micron is 10 to the minus 6th. Nano is 10 to the minus 9. The smallest particle this can filter is 1,000 times larger than the end of story. But think of how many people we put to work. Think about, and it's better, right? Our world is better because we're filtering everything bigger than 1 micron. So there's benefits, right? And if you just sold the benefits, look, we're circulating air. Some of the larger particles are going to trap some of the smaller particles. But that's not what we're selling. We're selling what they used to call it when the wagon came to town, and they had medicine. We're selling
Snake oil.
So there you go. I didn't say it. All right, so for visualization, we'll often rely on atoms equal balls models, right? So we represent things in cartoons that aren't exactly the way they look, but they're our best representation. And then we use colors to differentiate them, right? So here we have our biology, because you just can't get away from it now. And this was, look how old this is. This was 11, 12 years ago now, right? Carbon monoxide combined on the site, the hemoglobin normally carries oxygen. So that's the problem with carbon monoxide. That's why you get carbon monoxide poisoning. That's why we came up with detectors that we put in homes to keep people safe, right? All right. Hemoglobin carries oxygen. So now we're showing oxygen and the heme, right? And that's, people get excited about it because it's about their bodies and it's about their life. But there wouldn't be any of these studies if somebody wouldn't have defined oxygen and hemoglobin and iron and, all right. So everything builds on everything else, and that's basically the way your whole life's gonna run, right? The minute you start taking responsibility for your own education and finding out what you wanna know, don't ever stop. And don't limit yourself, go, well, I'm just a biologist, or I only wanna know about this. Well, yeah, to start with, and then you've got, what are you going to do for the next 40 years? Right? I do crossword puzzles, and I play Wordle now. It's great. All right, sulfuric acid on a massive scale. So how big is the chemical industry? It's huge, right? We have sulfuric acid, 70 billion pounds of sulfuric acid. Billion, how many is that? It's like 3, 6, 9 zeros. And then your number. Okay. Ethylene, C2H4, 50 billion pounds. So what do we do mostly with ethylene? We burn it, right? We do combustion with it. So we're putting 50 billion pounds of ethylene byproducts into the air, right? We use it for plastics, we use it for all kinds of things, but primarily we burn it. Propylene, same thing. I mean, we make plastics with it. We make antifreeze with ethylene glycol, but mostly we burn it. C2H4, right? So when we talk about C2H4, what we're talking about is, one too many. Got carried away. This molecule. When we're talking about propylene, right? We're talking about this molecule. And you can see they're very similar. They have double bonds. Maybe you don't know what double bonds are, but you know, depends on your level. And where to appropriately use them, and Lewis dots and all that stuff that we're going to cover again. Chlorine gas, I mean, we only use 21 billion pounds of that. 21 billion pounds, right? At a penny a pound, that's $21 billion. No, it isn't. I did the math wrong. At $1 a pound, that's $21 billion. At a penny a pound, you just take 100 off that, and it's $2 billion. So a $2 billion industry at a penny a pound. All right. Just to give you an idea how big this chemistry on a massive scale is. All right. So how do we start approaching it? Well, let's break it down in types of matter, right? We have physical states of matter, right? We have solid, liquid, gas, and they're temperature dependent, and they're reversible. We can go from one phase to another and back and forth. We can, what else can we do? Oh yeah, we can raise the temperature and drive it all the way from solid to gas. And what we like to say is it's determined on stickiness, right? How do the molecules interact together? Can you pull them apart? How easily do they pull apart? So a compound that's not bound very well can change states very easily. A compound that is bound strongly takes a lot more energy to expand or to change phase. And remember, it's perfectly okay to sleep in here. All right, just you're not gonna get in trouble. Pure substances, matter that has distinct properties and composition that does not vary from sample to sample. Although I might drop a book on your desk. Just saying, has happened. Matter that has distinct properties and composition that does not vary from sample to sample. So we have our classifications of matter. We have our physical states, liquid, gas, solid, plasma, supercritical fluid. We have pure substances with distinct properties and composition that doesn't vary. When we classify matter by its composition, we have elements that consist of one type of atom, can't be broken down into any simpler substances by physical or chemical means, which physicists now do break it into smaller parts, but they're physicists. Nobody understands them. Molecules, except for that one, Tyson Fury, no, that's the boxer.
Neil
Neil
deGrasse
Tyson
Tyson.
deGrasse.
Neil deGrasse Tyson.
Okay, there you go. That guy.
That's the physics dude.
That's the physics dude.
Yeah.
But he's relatable. He's like the Einstein of our time, right?
Yeah.
Because he gets to go to parties. He's the only physicist that's ever been to a party, except for Einstein. And he got to date Marilyn Monroe,
Yeah.
which at the time was a pretty good deal.
Oh.
You know, and then the Kennedys got involved.
Oh my God.
And you're never going to beat out a Kennedy,
No.
for God's sake. You know, I used to hope to be a Kennedy, that someday it'd be discovered that, you know, I was JFK's bastard child or something, but turned out I wasn't. But I used to think, wow, you know, I could be that successful. And so it just shows that your determination of success is based on your family, right? JFK Jr. ran a magazine that lost $1 million a month, and everybody considered him to be some kind of hero, right? I don't pay my gas bill, which is only like $35, and all of a sudden I'm the world's worst person. I don't know how that works. Because I could lose half that, sure, easily, 50. I could lose $500,000 a month, or a year, or whatever, 2 years, 5 years. And I'd feel pretty good about even having that kind of resource to lose that kind of money. Okay, so there's one type of atom. There's molecules that consist of 2 or more atoms that are chemically bound together. So elements, molecules. Compounds, composed of 2 or more elements which are chemically bound together. So elements, molecules, and compounds. Oh my. And elements, of course, are all listed on the periodic table, and the difference in elements is the number of protons. Because you could have the same number of electrons or neutrons. No? Yes. What about classifying these substances? Let's go. First one. What does it look like? Is it an element, a molecule, a compound, or a mixture? The one on the top left here.
Element.
Well, that was one viewpoint. Anyone else? All of you?
Element.
Molecule.
Molecule?
I see
Oh, yeah.
a single molecule.
Right here?
Yeah.
Yeah,
Molecule.
right?
That's
Yeah.
It's an element?
Is it?
Molecules consist of 2 or more atoms. You see 2 or more atoms?
Element.
It's an element.
Yeah.
Okay.
Element.
Don't get mad at me. You're right. That's right. It is an element. And see, that's the whole point, right? It's not about right or wrong. You throw something out there, see if it sticks. If it sticks, okay, great. If not, correct. You know what's better, actually shown to be better learning practice, to be wrong. Okay, I know there are a lot of people in here who've never been wrong, but it happens. And I mean, one way to be wrong is to actually offer an opinion and then not go, oh yeah, I was right, right? So you can be wrong in here. It's a good idea to be wrong because then you're locked in. So if you say this is a compound or a mixture and you're wrong, you're like, oh shit, I thought that was a compound, a mixture. You didn't wait until somebody said, oh, that's an atom, and you went, yeah, that's an atom. It's not the same thing, right? One is you went out there and you got it wrong and you went, oh crap, I gotta get that right. And the other is you waited until you knew what it was and you said, oh yeah, I knew that. That's what I like to do. Because you're never wrong. Okay, let's go to this one.
Molecule.
Molecule.
Molecule, there's two of them.
There you go. Molecule is 2. Stoichiometry, we're already doing stoichiometry. Why? Because we know that to make this molecule, there's two atoms. Right? Okay.
Compound.
Compound.
Why? Just because it's next on the list?
No,
So
there's
there's
two
two
or more.
different looking atoms.
One's purple and one is green.
See? Chemistry's so simple. I mean, it's amazing, right? Why do people build it up so big? I don't know.
It looks like a hole. Green purple. It looks nice.
You can make like a car out of it, right? I don't know. That's what I see everything in the car. Right? Uh-oh.
Mixture.
Yeah, why? Because it's got 1, 2, 3 different types of things floating around in it. Okay, so that's all there is to it.
Yeah.
Right? If we've got an individual particle, right, it's going to be an element. Right? If it has more, what is this again?
Molecule.
Molecule. And then this is
Compound.
compound.
Mixture.
But are there molecular compounds? Sure.
Yeah.
Oh, that makes it a little more. Oh, we need to memorize some element symbols right off the bat. They're easy though. CFHINOPS. I like to make not anagrams.
Mnemonic.
Mnemonics. How do you say it?
Mnemonic.
Mnemonic.
It's MN.
Please excuse my dear Aunt Sally.
But what about Johnny Memnonic? All right, it's a good Keanu Reeves movie. He puts a microchip, so they microchip him and they put information in his brain, and then he runs around and then delivers the chip out. His brain gets a lot of money, probably doesn't live very long. All right, so we have carbon, fluorine, hydrogen, iodine, nitrogen, oxygen, phosphorus, and sulfur. So that's just 3, 6, 8. Oh, I'm sorry, I'm just right now, I'm just doing that, right? I'm coming up with some kind of churlish freaks have invariable necrophiliac.
Oh my gosh, that's a lot.
I know, right? There's a lot to unpack right there, but that's how I remember things. And you should have seen me in anatomy. Woo. Yeah, you couldn't talk to me at all because it just came out of porn. All right.
Oh no.
So there's two things, a homogeneous mixture and a uniform mixture, and a heterogeneous non-uniform mixture. Well, that's pretty easy. So all we've got is, this is building blocks, right? We got solid, liquid, or gas. We've got elements, compounds, molecules, and mixtures. And mixtures are just either all the same or not all the same. Okay. And can you believe that took us like 6 weeks? And we're doing it all in the first day. Identify which of the following are compounds, which are elements, and which are mixtures. Here we go. Silicon. I don't have my ABCDs. This is an ABCD lecture. All right, so silicon.
Element.
Got one element. This is like a participate.
Compound.
What are you asking?
Is it an element?
Oh, mixture. Okay.
Yes.
Oh, okay.
Okay.
So now we're on board.
Everyone,
Yes.
So let's start. Is it an element?
Yes.
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 Okay.
Yeah.
Then salt. Oh, yeah, I gave you a periodic table first day. Didn't I?
Compound.
Should always have that ready.
Compound.
Salt compound. It says two things right here. Nozzle. Nozzle.
Element.
What about a diamond?
Element.
Isn't it carbon? Sure, there's a bunch of carbons.
Yeah, it's a whole bunch of carbons, right?
Bunch of very stressed out
Weak compounds.
Highly stressed carbons. Hey, did you get a highly stressed carbon for your fiance? No, but I am. Okay. Diamonds. Yeah. Well, okay. But it's the same
Element?
element.
Mixture.
It's not a mixture because it's one thing.
So it's an element.
Well, it could be a homogeneous mixture, huh?
Yeah.
Yes.
Could be. Well,
Homogeneous.
what did we say a mixture was, though?
Mixture.
Or
Multiple.
two or more elements can be bound together. So if there's
Two or more substances. This is only one substance.
But they maintain their separate identities.
Ooh.
like a superhero.
Who are you are so ways in the ways of science? All right. I don't know. What are we going to do with that? Two or more atoms that are chemically bound together. There you go.
Compound.
It's a molecule.
Hey, that wasn't
Molecule.
an option.
It's a molecule,
That
right?
was an option.
Yeah, you were right. It's not an option?
No. You said elements. make
Ah.
atoms.
Element and mixture, yeah.
Whoa.
Oh.
Wow, I'm sneaky little devil, aren't I?
But who put kryptonite up there?
Yeah, KP. On KP. See, it has a whole new meaning now to be on KP. It's not kitchen patrol anymore. It's Superman's deadliest weapon. Well, it's a made-up thing, isn't it?
Yeah.
Yeah.
Just be an element.
There's-
Same thing as diamonds.
Yeah, it's kryptonite. It's a mixture, right?
No, I think
Isn't it like a mineral from Superman's planet?
it's naturally occurring though, like diamonds.
Krypton.
Krypton's the planet. Kryptonite is might not.
No, but Krypton's the element, right?
No, Krypton's the planet.
Oh.
Planet Krypton.
What?
What?
I'm a nerd.
Well, you got to give it to the nerds. They know their business. All right, water.
H2O.
I hear a compound. Yeah, compound. Right.
Compound.
Yeah.
Say compound.
We're having some trouble here. What if I put water and silicon together?
That'd be a mixture.
Mixture?
There you go.
Mixture, yeah.
What about arsenic?
That is a
Element.
Smells like almonds. Oh wait.
No, that's cyanide. Bitter almonds. What? Have you ever had a bitter almond?
No.
Tastes nasty. You don't know until you're biting into them. All right. So arsenic is what little old ladies used to use to kill their husbands and rats.
And rats,
Yeah,
yeah.
rats. Well, same thing, right? Okay. All right. Wow. Sorry, guys. Threw us under the bus there. CO2. Some of us, the husbands anyway. CO2. Yeah. Right. Two elements. Compound. CO2, water, and kryptonite. What about granola?
Mixture.
mixture.
Yeah, sure. What's in granola anyway? Depends on who makes it, but
Yes.
Wheat,
Oats?
almonds, oats.
brown sugar sometimes.
Yeah. M&M's are good.
What?
Raisins.
Raisins.
Oh.
Oh, kind
Oh,
of.
What are you from California? All right.
Sun-dried raisins.
Like
What?
granola bars, they put like raisins in that.
Yeah, sure. You can have raisins in your granola. I would-
I don't like them.
Oh, there we go. So you're anti-raisin. But California, we're pro-grape. All raisin, dried grapes, fermented grapes.
Fermented grapes are good.
Delicious.
As a matter of fact, let's have one now. All right. Granite.
You skip wood.
Skip wood.
Wood.
Yeah. Almond.
Silence.
And
Wood.
element?
Element.
No, there's no wood.
Compound?
A mixture?
Ooh.
Compound.
Well, what about there's so many different kinds of wood, right? So wood describes a substance that has matter composed of many different elements.
A mixture.
It's a mixture. It's a mixture. Wood is a mixture. But isn't it like earth, air, fire, water, wood?
That's a band.
What about granite?
Compound.
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 Aren't there different types of granite and don't they have
Yeah.
different,
Some
Mixture.
has
Mixture.
iron,
right? It's a mixture. Because it's what are those things that geologists look at?
rocks.
It's a rock. That's right. It's exactly. So that's what we do, right? Our level of understanding of something is based on the words we know to describe it. So as we proceed through here, we've developed a little tiny vocabulary already for staying. Right? Compounds, mixtures, molecules, homogeneous, heterogeneous, liquid, gas, solid, to describe things. And that's what we're doing. Then we switched over here to geology, and none of us know anything about minerals. Right? Or we're pretending like we don't for my benefit, so I appear to be more intelligent than I am. Helium. Have you had this class already?
No, I've taken chemistry before.
So there was a variation in definitions. Helium, yes, element. What about air?
Compound.
Okay.
Compound mixture. Oh.
Compound mixture.
Compound.
No,
It's an element.
it's a mixture. It's a,
Is it?
it's a heterogeneous mixture all the time, right? The air in this room changes every time one of us takes a breath. We change the relationship between oxygen and carbon dioxide. We pull a little oxygen out, put a little carbon dioxide in, a little bit of outside air mixes in, changes the composition. So every time we inhale or exhale, we're changing the composition, so therefore, it's not a homogeneous mixture. If you isolate the air inside here, is a homogeneous mixture. Because it's uniform. It's not changing because it's sealed. If you open it up, now things can move around, now they can change, the relationship. Remember, gas molecules aren't bound together, they float, well, you don't remember necessarily, but gas molecules aren't bound together, so they float around, so they can interchange places. Some oxygen can be here, some CO2 can be here, some nitrogen can be here, and then they can move all around. And then when it's trapped in that space, it's now different than it was before. But overall, on the planet, we say that the ratio is fixed and it's uniform composition. But the reality is, that's just the giant picture. The microscopic picture is it's constantly changing in any one space based on how much plant life there is, right? So let's just do a check. If a tree eats CO2 and spits out oxygen, how do you get rid of CO2?
Said the tree.
The tree.
Grow more trees.
You grow more trees. How do you increase CO2 in the atmosphere?
Cut down trees.
Cut down trees. Now, if you say that out loud, it sounds like you're simplifying the issue. But you're not, right? Every time you put in a sidewalk, you pave over something that provides oxygen for the planet. That's all. All we got to do is make breathable concrete. Have the concrete suck it, mix in some biodiversity in our concrete.
That's
Anyway.
so the little weeds grow through the cracks.
Yeah, right.
No more birds.
Yeah.
I think you're onto something on that breathable concrete.
Except it's porous, put a crackboard.
Yeah, that's a billion
That's not
dollar.
his problem.
Well, I mean, that's just an engineering problem, right? Not my deal. I came up with the idea. All I do is come up with ideas. Somebody else has to implement them. God's sake, that's why you have a doctorate. It's a philosophy. I approach problems, I give you a solution, and then you try to figure out how to implement. There's a famous organic chemist, the guy who came up with, who made the first organic compound, and he was talking to somebody, and they said, "Oh my God, that's a lot of labor." And he goes, "That's what we have other people for." So you got to remember where on the hierarchy scientists used to be compared to where they are now. So it used to be the guy that had all the resources would make that building and go, "That's my science lab," and then he'd get a bunch of guys to do whatever he told them to do, and then train them, right, so that they could make a living. All right. Can you use a decision tree to classify matter? That's a good idea. Matter, does it have constant properties and composition? Yes, then it's a pure substance. No, then it's a mixture. So one of the reasons we say wood is a mixture, right, is because it doesn't have those things, right? It's not a pure substance because there's so many different trees and so many different ways of looking at wood, just saying the word wood. Is it uniform throughout? No, then it's heterogeneous. Is it uniform throughout? Yes, then it's homogeneous. And so that's, just because we can't see the mixture of air doesn't mean it's homogeneous. You don't have to be able to see the difference for there to be a difference in composition. Generally, when we associate heterogeneous, we say, oh, it's heterogeneous because we can see that it's not we can see that it's not uniform. So pure substances, can it be simplified chemically? No, then it's an element. Yes, then it's a compound. All right. So that's our little decision tree if you need one. Again, we're not going to do a 100-point question on this, but it's good to be able to identify it, and some discussion of it's always fun, I think. And because you can, like the diamond one, that's a good question, right? And the same thing would be apply to buckyballs, which are C60, right? But the C60 with an H on it. So now all of a sudden you know it's a compound. Okay, so we're in a lab. This is classic, right? This goes back to the 60s, I think.
Okay,
1960. Okay, shoot. Does it move? Yes. Should it? No, duct tape. Yes, no problem. Does it move? No. Should it? Yes, WD-40. No, no problem. Okay, so that's how you work in lab. I like that. Chemical won't be on the test though. Sorry. There's another one called ducket, and we don't say that one anymore.
It's not a good thing.
Yeah. Physical changes. Okay, so this was brought up in class. Changes in physical state or appearance, but not involving making and breaking of bonds. Okay, we haven't even defined what bonds are, but bonds are what holds things together. And if you break them, it's a chemical change. Or if you make them, it's a chemical change. So if you fall in love, you're making a bond, right, Nathan?
Yes.
Yes. Now, that bond might be cationic now, or anionic, or it could be two cations and you repel each other, right? So you gotta be careful whether you're making bonds or breaking bonds, right? But the substance itself remains unchanged, so that's a physical change. So if you just change state, change temperature, those are physical changes. Chemical changes involve the making and breaking of atomic bonds. The substances change. What is happening at the atomic level? That's the question, right? This is a question-based class, question-based inquiry. There's a lot of math, but that's not really what chemistry is. That's just bookkeeping and record keeping. And the bean counters have taken over. And for me, solving problems isn't as interesting as asking what's happening and trying to solve that problem. Physical properties. So what doesn't change the chemical properties? What doesn't change the chemical properties are physical properties, and what that's going to be is color. Like, so if something's red, that's not a physical change. Melting point. If it was a solid and we found a temperature and now it's a liquid, it's not a physical change. A boiling point. If it was a liquid and now it's a gas, we haven't broken any bonds. We've broken what we call intermolecular forces, but those are not bonds. The identity is unchanged. Density, right? What something weighs. So yesterday in lab, with the other lab I'm doing at a different school, it's organic lab, we were doing these things called separations. And you have two layers in a separation. And we did it several times, and the question came up, which layer is going to be the aqueous layer this time? Is it going to be on the top or on the bottom? And the answer is, the densities don't change ever, right? So if the first time you use something and it forms water and this other phase, and the other phase is on the bottom, every time you do it, that phase will always be on the bottom, because the density of what you're looking at doesn't change in its ratio. So if the density of water is 1 and the density of methylene chloride is 1.33, right? The question is, if you put it in a flask and you have water on the bottom, oops, you won't, water on the top, and then 1.33 on the bottom with the CH2, Cl2, right? Every time you do it, when it separates out, the more heavy substance will be on the bottom. There's no chemical change taking place, just the relationship stays the same because the densities of each individual compound stay the same. And that is the kind of questions that answer what happens. You can go into the math if you're some kind of, I mean, we're gonna have to go into math, right? We all have to do the math. But the idea is, I would much rather have you understand what's going on with the density, because now you're solving problems. You're not just doing mathematical solutions, you're not just memorizing formulas, you're understanding the basic concepts of explaining the universe. And the universe says that if something has a certain density and you put it with something else of a different density, the one with the more density is going to be on the bottom every single time. That's like a law, right? That's something we can reproduce over and over again. Do we know why? No. We don't know why certain things have more. We can try to explain it. So a law is something that we observe, but it doesn't explain why it occurs. So chemical properties are interactions, transformations into other substances such as flammability, corrosiveness, reactivity, right? So, yeah. What happens when we burn something? That's my favorite question. What happens when we put something in a container and it has so much energy it can't stay in there? It's another one of my favorites. Reactivity. Right? What happens when it comes in contact with oxygen? That's one of my favorites as well. That's how I blew up a lab, right? Working on this little line, lab's about as big as this, little gas line, it's about this size. There's a little tiny flask here, and you're starting a reaction. And my buddy's standing right here. He's got the syringe. He's putting, like, well, you guys, it's a very small amount, a microliter syringe. So the whole thing holds 1 microliter. And we're putting a drop out of the microliter syringe in there and watching it spin, and it's minus 140 or something, 170. We're cooling it with liquid nitrogen. It's just a little tiny flask. Drop. And when the reaction takes place, drop, and you're spinning and you got the solution. Drop. And usually it only takes 1 drop, and we're at 3. But it's just sitting there, nothing's happening, nothing. And he goes, 1 more, and I go, okay, boom. And he puts that drop in, and it shoots from whatever the bottom was, like minus 170, all the way up to 40. And it's just a little flask. And I'm like, it's gonna blow. You know, I do that, some theatrical thing, and I push him away, and the thing just blows up. And I mean, this little tiny flask, embedded stuff on that wall back there, right? And on the way there, it took out everything. Fortunately, they didn't come this way except to spray me with like acetone or something, and which when it comes off, you feel really cold. But the idea is that it wasn't our fault, right? We were doing everything we were supposed to do. We were waiting between drops, we were stirring, but that one time, for whatever reason, on a reaction we'd done 15, 20 times, didn't go the way we thought it was going to go, for whatever reason. It's like when the space shuttle blew up, right? Lots of really big flights. A lot of people, it seemed like it was the safest thing in the world. And then all of a sudden, one little 29-cent part failed, and a bunch of people died. And it's dangerous. Like, you get up, when you're an old guy and you get up on a ladder, right? The chemical reactions that hold your muscles still sometimes just stop working. And then boom, you fall off the ladder and everybody goes, I told you so. That hasn't happened to me yet. But, you know, it's probably in the future. I mean, as long as I don't say, oh, it won't happen to me. All right, so here we go. Where are we now? Still got a few minutes left. Right? How long do we go to? 150? Let's take 10 minutes. Take a hike. Go outside. Come back in. Please. One or more of them. Physical, chemical change. I hear one physical. I need some backup. We're committed.
Physical.
Physical. All right? I got to hear it a whole bunch of times. So this is the way science works. It's by consensus. You get a bunch of educated people in a room. They decide what is going to be the way they agree on it. And can they agree? And if you have a big, strong leader in the front of that group, like they did with Boyle and all kinds of chemists in the past, change is very, very, very slow, because if that guy decides that it's not that, all his allies agree with him.
Yeah.
Right? Regardless of what the facts are coming up, all the guys agree with him. Okay.
So we're stuck with two-party system.
Wrong class. All right.
Sorry, no.
The social ills will not be healed as long as there's mankind, is my opinion.
I do have.
But that's not definitive. It's just observational. It's what history is. It's filled with the same thing happening over and over. Only this time I think the rich are in solidarity, and there will be no coming back. All right. So, AI. 2 words. Yeah. They don't need humans anymore.
Yeah.
Electrolysis in water.
Chemical.
Why?
Because you're taking two different compounds and then, or molecules, and then turning them into.
And what do we call that? What do we call when we take one thing and turn it into something else? What do we do?
You're splitting them.
Okay, get closer. Simple term.
Breaking the bond.
There you go.
Breaking bonds, yeah.
Thank you. Breaking the bonds. That's how we know. If the bonds are not the same as they were, it's chemical. OH bonds are broken, HHOO bonds are made. Good. In principle, all mixtures can be separated by exploiting physical or chemical differences. We were talking about that, right? So if you have a mixture and part of it's solid and part of it's liquid, you run it through a filter. And on the other side, you get the liquid, and on the paper side, you get the filter. And now all of a sudden, you've done a not chemical process. You've done a physical separation. Another way you can do it is if you have 2 liquids, you take advantage of the difference in their boiling points. You turn them into gases, and they separate themselves. And as the gas goes up, it condenses and comes back down on the other side. And now you've separated a liquid. Distillation, that's famously known, that's how the Kennedys made their money, right? Their dad was a rum guy. He would make rum during the Great Depression, back in the 20s, 100 years ago now. And profit for that. Where stock car racing came from, which I love. For some reason, apparently a guy from the South. And I'm not, but I still love left turns. Okay, chromatography is another way to separate things. Liquids travel through different mediums, which is like sand. Let's just say you had sand. Certain liquids travel faster through the sand than others. And we use that principle to separate them from each other. Organic chemistry is a lot of chromatography, because things turn left-handed, they turn right-handed, and you can separate them based on what we call chirality, which is that left-hand, right-hand turn. Scale removal, from lime deposits on your shower door. Refining, which is just really another type of distillation. Okay, so we've determined all those things, and we're done. We're going to stop right here and make it.